Okay, I think here it is on the hour, so I guess we can start. Presumably we are live on YouTube right now as well. So hello everyone and welcome to this month's iteration of the Rocky Worlds discussion. My name is Libel Christmas and I'm at Uppsala University in Sweden, and I will be your host and moderator tonight. And today we will be listening to Renyu Hu of JPL Caltech, who will be talking to us about JWST thermal emission spectroscopy of the super Earth 55 Cancri E. So as a reminder just of our netiquette, it would be good if you could use your full name on your Zoom name and keep yourself muted throughout the talk, and then we'll be taking questions at the end. And you can either ask questions just by raising your hand, video, or with the function. In which case we encourage you to turn on your video so that we can say hello to you before you unmute to ask your questions. But if you're not able to do that, of course, you can also drop your question in the chat and we'll just read them out. So with that being said, I'm going to now hand over to Renyu. So please take it away.
Let me share my screen first. All right. Can you see my slides?
Looks great. Thank you.
Awesome. All right. Thank you very much for the introduction. And it's really great to be here. And it makes me really happy to see that the community looking into characterizing rocky exoplanet has become larger and larger. And I think that this series of online forums seems to be a great way to connect us all together in this field-defining pursuit to understand rocky planets in a broader context. So since the discovery in 1990s, exoplanet has been inspiring the exploration of the universe. So today we already know planets of Earth's size. We also know planets that receive irradiation from their host stars, Earth receive from the sun. We also know many planets that populate the parameter space that is not populated in the solar system. The diverse mass, radius, and temperature on the small planets discovered today means that they probably have diverse compositions. So here is a plot from a recently published paper, and it summarized the small planets that have well-measured mass and radius. And we can see that many planets, particularly those with radius less than 1.5 Earth radius, follow this mass-radius relationship for Earth-like composition. And many of the larger planets, however, have densities that are substantially lower than what it would be for an Earth-like composition. And their low density indicates that they have substantial volatiles by mass, either hydrogen or water. There seems to be also a continuum from this volatile-rich planet to the rocky planets, and that's making us wonder what does that mean to the evolution of planets in general. So focusing on the rocky planets, they do not have a massive volatile envelope, but they can still have an atmosphere, particularly a high mean molecular weight atmosphere, like we do. The size of our atmosphere is on the order of, the vertical size is on the order of 100 kilometers. And on a hotter planet, the size would basically scale us the temperature. So on this plot, it's easy to hide a substantial atmosphere without making the planet substantially larger. So these rocky planets cover a wide range of size and temperature. And as a sample together, they provide us the unique opportunity to test our understanding of planetary evolution. So we can ask these basic scientific questions about these planets, whether they have an atmosphere, what are their atmosphere or surfaces made of, do they have volcanism if they're a solid surface planet, or if they have a magma ocean, what is the composition of the magma ocean? So for instance, it is widely hypothesized that rocky planets in the solar system, Earth, Mars, Venus, have experienced a phase where the planet surface so hot and that it is completely molten and becoming a magma ocean. And we think that the evolution happening in this phase has a lot of bearings on the outcomes, the outcome atmospheres that this planet eventually have. But we don't have an ongoing magma ocean on any rocky body surfaces in the solar system, for us to see today. So instead, some of the rocky planets, in these samples, have such a high equilibrium temperature that they have a permanent magma ocean, and this provide us the opportunity to observe an ongoing magma ocean and its interaction with the atmosphere. So I consider characterizing rocky exoplanets and their atmospheres a frontier of exploration of the universe, because it really provides us the opportunity to test this series on atmosphere interior interaction and planetary evolution in the regimes that do not exist in the solar system. So over the past decade, the observational search for an atmosphere on rocky exoplanets was pursued by Spitzer for several targets, which results in some important clues about whether they have atmospheres. JWST has really provided us the revolutionary capability of obtaining precise measurements in the thermal infrared. And that has been applied to several objects as well. So today I will use the observation of this iconic rocky exoplanet 55 Cancri E as an example to demonstrate how we leverage JWST's capability to detect and perform initial characterization of a rocky exoplanet's atmosphere, and also how mid-infrared spectroscopy, also enabled by JWST, can tell us about the surfaces of a rocky exoplanet, even if they do not have an atmosphere. So when we think about determining whether a rocky exoplanet has an atmosphere, the first thing that might come to mind may be spectroscopy. Well, before JWST, we have not had very good spectral resolution or wavelength coverage on small planets. Alternatively, we, at the time, either myself and several other colleagues have realized that a rocky planet's thermal emission measured either in secondary eclipse or as phase curve can constrain whether it has an atmosphere. So this diagram shows the main process that needs to be considered in this problem. So the stellar radiation is the energy input. It comes in from one side, assuming that the planet is tidally locked. Some of those energy is reflected, but some is absorbed. The absorbed energy will be radiated out as thermal emission or transported to the night side and then radiated out as thermal emission over there. So we can define two timescales. One is the radiative timescale, and one is the advective timescale. So if the radiative timescale is much longer than the advective timescale, there will be sufficient time for energy to be transported from the day side to the night side. And thus, the heat redistribution on the planet is efficient. The temperature difference between the day side and the night side will be small. The temperature will be relatively lower on the day side. So as a result, if you observe the planet in secondary eclipse, you will see a lower flux. And if you observe the phase curve, you will observe a flatter phase curve. On the other hand, if the radiation timescale is much less than the advective timescale, the heat redistribution will be inefficient. So the temperature difference between the day side and the night side will be large. The day side will be hotter. So if you observe the planets in secondary eclipse, you will expect a larger flux and also a larger phase amplitude. So now we can think that the advective timescale could be approximated by a ratio between the size of the planet and some characteristic velocity of the energy transport. This lumps all the complexities of atmospheric energy transport that will happen either by advection or by waves. But previous studies have shown that this characteristic velocity will be very, very small if the transport is done by motions in a molten lava, while this characteristic velocity would be much larger, would be many orders of magnitude larger if there is a substantial atmosphere. So this advective timescale would differ by many orders of magnitude between an airless planet, even if it has a magma ocean, versus a planet that has a substantial atmosphere. So this is distinguishing, and this is where the distinguishing power comes from when we use this method to characterize whether a small planet has an atmosphere. So the day-side thermal emission flux has been measured for a number of rocky planets. So in this plot, I put 55 Cancri-E in context of other rocky exoplanets that have published the thermal emission measurements, comparing the measured brightness temperature with the day-side equilibrium temperature. So strikingly, for most of the planets in this sample so far, they observed the brightness temperature match exactly with the expectation for a fully absorptive sphere without any heat redistribution, essentially a dark rocky ball. So the Spitzer measurements of 55 Cancri-E and K2141b, the two hottest planet in the sample, suggest some deviation from this one-to-one line. But the error bars of these measurements are large and the results are inconclusive. For 55 Cancri-E and LHS3844b, we have also measured their thermal emission phase curve using Spitzer. And we have learned something very interesting about this planet. So 55 Cancri-E is about 1.8 Earth radius and has an equilibrium temperature of over 2000 K. And using Spitzer, we have measured its thermal phase curve at 4.5 micron. And the initial data analysis of the phase curve has shown that it has both a substantial magnitude and also an offset between the peak of the phase curve and the secondary eclipse. So we have developed this retrieval mechanism to retrieve from the phase curve and determine what that tells us about the radiative timescale versus the advective timescale expressed by this ratio here. And the result is that the phase curve indicates that the radiative timescale and the advective timescale on this planet are on the same orders of magnitude. And this implies that the planet should have a substantial atmosphere. We can even derive that the atmosphere should be approximately larger than 1 bar. And that motivates us to apply for JWST time to study its atmospheric composition. There has been a reanalysis of the same data set, which instead suggests that the phase amplitude would be larger and the phase offset would be negligible as opposed to the original analysis. So the conclusion from the Spitzer phase curve alone has been inconclusive. On the other hand, for LHS3844b, which is a 1.3 Earth radius planet and it has a lower equilibrium temperature just below 1000 K, its Spitzer phase curve shows a large amplitude and without any offset. And using the same retrieval framework, we have determined that its radiative timescale has to be smaller than the advective timescale. And this is consistent with the atmosphere, with the planet does not have any atmosphere. So the rocky planet LHS3844b is likely a bare rock planet, and also its surface should be quite dark. Motivated by this work, we have also applied for JWST time to study its surface composition, which I will talk about in the second part of the talk. So using JWST, we have recently observed the secondary eclipse of the planet 55 Cancri-E. we have two visits. The first visit using our NIRCam covering a spectroscopy between approximately 4 to 5 micron, and another visit using MIRI low resolution spectroscopy covering 5 to 12 micron. So these data sets are quite challenging to analyze. It's probably more challenging compared to the other JWST data sets I've seen. And this is mostly because of the brightness of the star. So the star has a weak magnitude of about 5, so it's a borderline naked eye visible. And because of that brightness, we had to use a small number of groups per integration in these observations. And these demands customized data analysis pipelines to deal with. So I could talk about some these aspects more later, but at the end of the day, we have 4 independent analyses for NIRCam and 2 for MIRI, and they are generally consistent with each other. Here, I'm showing you the detrended light curve from these observations. So you can see that in the NIRCam light curve, it shows quite a bit of correlated noise on the time scale of about an hour, which is the same time as the eclipse, and with a magnitude about 50 ppm. And this prevents us from deriving a measurements of the eclipse depths in the NIRCam band. Instead, this correlated noise do not exist in the MIRI light curve, and from which we can derive a precise measurements of the eclipse depths. So based on the eclipse depths, which measures the flux from the planet, the thermal emission flux from the planet, we derive a equilibrium temperature from the MIRI bandpass. And if we put that equilibrium temperature on this plot, we see that the measured brightness, this brightness temperature, we see that the measured brightness temperature is lower than what you would expect for a bare rock planet by 8 sigma. And this by itself means that the planet cannot be a bare rock, and instead must have efficient energy transport from the day side to the night side, which lowers the temperature, or it could have gas absorption in the MIRI band that lowers the brightness temperature observed in that band. But both would require a volatile-rich atmosphere. So I think that this single data point is already a very strong evidence for that rocky planet has a substantial volatile-rich atmosphere. And we have also simulated a series of molten lava surface models, which assumes various rock compositions and self-consistent vaporization atmosphere in equilibrium, and confirm that all of these scenarios are excluded by the MIRI observation with very high confidence. So we're not giving up on the NIRCam data. So turning back to the NIRCam data, while we cannot obtain an absolute measurement of the eclipse depths, we found that if dividing each of the spectroscopic light curve by the white light curve, the time correlated noise will be reduced to well within the random noise. This implies the achromatic nature of the correlated noise that we have seen. So we thus derive a relative eclipse depth spectrum based on this spectroscopic light curve divided by the light curve for the NIRCam part. And here in this plot, I show the relative eclipse depth spectrum. So in this procedure, we lose the information about the absolute eclipse depths, but we retain the information about how the eclipse depths change with wavelengths or the shape of the spectrum. So the shape of this spectrum is also consistent with the shape that we will get by directly fitting the spectroscopic light curve minus an offset, which indicates the validity of our approach. So let's put the spectrum together. Remember that the NIRCam part of the spectrum is a relative measurement with an arbitrary offset, and we can derive an absolute measurement from the MIRI part of from the MIRI band. And then Putting these two parts of the spectrum together, we use a retrieval framework to see what kinds of atmospheres that would fit the spectrum. So we perform a black body fit to establish the null hypothesis, and then carry out model fits that include various potential molecules. Among these, using carbon dioxide or carbon monoxide as a single gas composition or as some binary mixture between CO2, CO, and nitrogen will result in models that are prefer over the null hypothesis by approximately 3 sigma. So the best fit models shown here indicates an atmosphere that is about 1 bar, about 1 to 100 bar, that contains substantial amount of CO2 by volume mix ratio more than about 10 to the minus 5. And in this correlation plot, the correlation between the volume mixing ratio of CO2 and the surface pressure indicates that the spectral modulation here in 4 to 5 micron constrains the column density of CO2 in these models. And also the posterior of the CO2 has a tail towards a small mixing ratio if carbon monoxide, CO, is assumed as the background gas, which indicates that a CO-only scenario is also possible. So to further study the range of physically plausible atmospheres on the planet, we have carried out two sets of self-consistent atmospheric models. So in one set of the model, we assume an atmosphere will be in the solution and chemical equilibrium with an underlying magma ocean. So these aspects of models, we leverage the progress in the geochemical community in the recent years. So in this case, the overall volatile content of this atmosphere magma system and the redox condition of the magma can control the atmosphere size and composition. And we have also found that just assume a volatile content of Earth's mantle and apply that to 55 Cancri, and using the local conditions there in terms of the size of the planet and the temperature, the atmosphere that would naturally come out from this type of models would be approximately 100 bar. And these atmospheres would naturally have some amount of carbon monoxide and carbon dioxide in it. And over a wide range of oxygen fugacity, these group of models actually fit the JWST data very well. And they are remarkably consistent with the preferred scenario by spectral retrievals. We have also considered some variant scenarios. For example, if the planet has lost most of its volatile, completely lose its hydrogen, but retain 1% of the carbon and other volatiles, this could also result in a smaller, about 1 bar atmosphere, but also consistent with the observation. Alternatively, in a broad sweep of parameter space, we have simulated over 3,000 self-consistent atmosphere models covering C, H, O, and SP abundances, and we form a little grid to see which combination of gases that will provide a fit to the model. And the best fit models also center around CO2-rich atmospheres or CO-dominated atmospheres. And in this broad sweep of parameter space, we also found that the presence of water, sulfur dioxide, and sometimes phosphine can improve the fit to the spectral modulation seen in between 4 and 5 micron in some cases. You may ask, what happens to this higher data point? So this gray line is showing the Spitzer observation in 2012, and that is obviously much higher than any of these models, what these models would predict. So we have considered that questions, and one idea that we have is that sometimes you can have enhanced emission of UV and visible absorbing elements from the magma ocean to the atmosphere. And this includes the sodium, potassium, magnesium, and other rock-forming elements, and they're typically absorptive in the UV and visible wavelengths. And if we have a substantial mixture of those things in the upper atmosphere, according to the self-consistent model, this would result in a substantial temperature. This will change the PT profile substantially and sometimes results in a temperature inversion. So when this happens, we can turn the dark blue model into a light blue model for the same, molecular abundances. And as a result, the spectrum, particularly in this 4 to 5 micron band, the shape of the spectrum and the amplitude of the secondary eclipse would change very substantially. So just to quickly summarize the 55 Cancri E part, this super Earth has a substantial atmosphere, and it is probably sustained by a magma ocean down below. So I'm putting here the travel poster. I think this is one of the famous travel poster for 55 Cancri E. And my friends at the NASA Exoplanet Exploration Program has told me that because of this paper, they may actually have to revise this travel poster. So stay tuned for that. Now we have an example where you have an atmosphere sustained by a magma ocean. Let's turn into another rocky planet, LHS 3844b, which from the Spitzer observation, we know that it's likely a bare rock without any atmosphere and with dark surfaces. So here I'm going to talk about some models and speculate on what JWST could tell us in the next year or so. So for this bare rock planet, and LHS 3844b is not one. It's not a single one. There's a growing sample of rocky planets around M-dwarf stars that seem to have little to no atmospheres, and they seem to fit the ideas that the atmosphere loss is particularly strong on planets around M-dwarf stars, and they tend to have little atmospheres. So for these bare rock planets, I have pointed out in 2012 that their atmospheres are their surfaces are detectable through prominent SIO features in the thermal emission band between 7 and 13 micron. So this method, this kind of measurements was inspired by the success using thermal emission spectroscopy to characterize the surface mineralogy and geology of rocky bodies in the solar system, such as Moon and Mars and many other rocky bodies. And in 2012, I proposed that this method can be applied to rocky exoplanets without any atmosphere. And now we have this this target is favorable for observations. For example, for LHS 3844b, we found that the surface types the surface types that can be consistent with the Spitzer observations will include the ultramafic surfaces, basaltic surface, or granitoid surfaces, and they tell us different stories about the geology on this planet. For instance, if the planet is really made of an ultramafic surface, that would imply that it has passed the magma ocean or high temperature volcanism that is quite recent. And if it has a basaltic surface, it will tell us that the planet has the secondary crust from volcanism that is more Earth-like. And the spectral features of these surfaces are detectable in the MIRI bandpass. So we can use the MIRI observation to try to tell apart these different kinds of surfaces. So in general, I'm very excited about this first look into an exoplanet, a rocky exoplanet surface composition, because this kind of information will provide substantial constraints on the geologic history of this rocky planet. Just one closer look in the spectral features. So on the left, I'm showing you the brightness temperature that we simulated on this planet, if we assume that they have different kinds of rocky surfaces, and I would like to draw your attention to this peak of the emissivity or the peak of the brightness temperature between 7 and 9 micron. And this is known as the Christiansen feature. And the wavelength location of this Christiansen feature is known to be a fairly unique and clean-cut tracer of the type of silicates. So you can imagine there's hundreds kinds of basalt and hundreds of maybe a lot of different kinds of ultramafic surfaces. And they all have different albedos and spectral features in detail, but their Christiansen feature, the location of the wavelength location of the Christiansen feature are fairly common among each broad type of rock. So the wavelength location of the Christiansen feature quite uniquely trace whether a surface is mafic or felsic. So we can use that to have some broad characterization of the silicate types on rocky exoplanets without going into much details. Recently, we have also collected new measurements with a goal to broaden our spectral library for rocky exoplanets, and we are expanding the range of rock type, composition, and texture. And we have selected these samples. And quite importantly, we have conducted lab measurements of these samples at higher temperatures. So you can imagine that most of the spectral library that we rely on has been based on room temperature measurements. And most of the exoplanet that we have seen today would have a temperature, surface temperature much higher than the room temperature. So in this work, we select those samples and we measure their reflectivity and emissivity under not just the room temperature, but also elevated temperature in collaboration with this group in Berlin, where they have set up this very nice experimental apparatus originally designed for characterizing rocks under Venus conditions, but we can also turn that into better understanding the spectroscopy of rocks for high temperature, for the temperature for exoplanet that has higher than room temperatures. So here is some initial results that we have. We found that the albedo of a rock type can vary widely within each broad composition classes. So for instance, on the left, I'm showing 3 kinds of ultramafic material, and they have very different reflectance in the visible light. And also, we also found that the albedo can vary also greatly with the grain size or the texture. So on the right, I'm showing you a granite, but between the powder or crushed or slag surface, their reflectance could also change substantially. So because of this composition and texture that has great impact on the albedo, in turn, we think that just from the albedo, it's actually very hard to tell what kind, tell the composition, tell what kind of surface that we are seeing, because within each broad composition class, you can have a wide range of albedos. So instead, we propose that in order to identify the composition on a rocky exoplanet surface, that we really need spectroscopy, for example, through that Christiansen feature. So in conclusion, the Super-Earth 55 Cancri E has a substantial volatile-rich atmosphere, probably sustained by magma ocean. And the thermal emission measurements from JWST can determine whether a rocky planet has an atmosphere. And if it has atmosphere, it can determine its atmosphere composition. And if it does not have an atmosphere, this also gives us the opportunity to characterize the surface composition through spectral features. In general, I think that many of these thermal emission observations of small, rocky exoplanets will have limited spectral resolution and signal-to-noise ratio. So it is probably not someplace where the detailed spectral retrievals can provide us a lot of constraints. Instead, I think that the self-consistent models that consider the interaction between the atmosphere and the interior would be more helpful, because these self-consistent models would be eliminating the parameter space, and it will eventually improve our ability to compare with the data and characterization of these exciting rocky worlds. With that, I'm happy to answer any questions. Thank you.
Thank you so much for that great talk. I think we should really get on writing that proposal for some kind of exoplanet sample return mission. But until then, we're very grateful for spectroscopy, and that spectral library looks really useful. So with that, we'll open for any questions. I'm going to give people an opportunity to maybe raise their hand. And if so, if you want to turn on your video and unmute. I see the first hand I saw was Yang Shan. So yeah, go ahead.
Very nice talk, Renyu. Thank you so much. I have a question. So I think some earlier studies showed that silicate clouds may form on 55 Cancri E, and silicate clouds potentially can have a high albedo. So have you considered that when you infer there's is a secondary atmosphere?
Yes, we have considered the potential high albedo scenario. So first of all, in order to be consistent with with the brightness temperature measured, the albedo has to be very, very high. And that high albedo overall is actually inconsistent with the visible light observation of the system. So there has been extensive observation by TESS and also by KEOPS, and they have not consistently found the eclipse, and that has put a fairly tight upper limit on the optical, band albedo of the planet. And second, I think that in order for the silicate cloud scenario to work, you still have to have an atmosphere to for the cloud to operate. But I do want to add that the silicate clouds might have to do with some of the variability that we are seeing in the mid-infrared. Especially there is a concurrent JWST program looking at the same system. I think the paper is coming out pretty soon. I think the main message there is about the variability. I won't be talking too much about that, but I think that the silicate clouds could be one of the reasons that we see a lot of variability in the mid-infrared brightness temperature for this planet.
Thank you.
Thank you very much. I think the next question was Joanna. Please go ahead.
Hi, Renyu. Thank you for a wonderful talk. Very exciting results. I'm sorry if I missed it, but I was curious if you could say a little bit more about the customization that you needed to do to be able to extract the data from such a bright star, and whether you're exploring any other ways to mitigate the systematic noise in these or future observations.
Yes, so we have tried a number of things about the systematics, but I would say that we wasn't be able to ascertain the origin of that noise. It could still be instrumental, but there is a possibility that what we are seeing is astrophysical from supergranulation on the stellar surface. So we have for the yeah. In addition to that, there is actually quite a big overall trend in the light curve, where we have tried a number of things to remove. You can fit it by in the standard procedure using some exponential or combination with linear. But we also found that it is correlated with some telemetry data that you can download as auxiliary information from the observation. So particularly in this case, we found that it's correlated with the temperature of the detector. And if we use the temperature of the detector to detrend, that would also result in a nice removal of that overall trend. And in addition, we found that sometimes the pointing has some issues, and the standard, for example, Eureka pipeline, in this case, does not give us the correct X and Y information. So we have to write our own code for that.
Great, thank you so much. Do we have any other questions? Maybe in the chat. Yes, I see one from Rob. Go ahead.
Thanks. Thank you so much for this really interesting talk. It was really cool to see everything, especially the spectral features of rocky exoplanet surfaces. I find it really interesting. But I have a question about that, because you really approach it as discerning between these different lithologies, between the ultramafic lithologies and basalts. But a basalt is not just a basalt, it's a collection of several different minerals. So to what extent can you really discern between different kinds of basalts with like different spread proportions of minerals? Because you also mentioned that the Christensen feature doesn't really vary much within a basalt. It mainly differs between different mineralogies. But then what exactly is the driving factor there? Is that the most abundant mineral, or is it certain mineral proportions?
Yeah, so for instance, in that expanded library, we have selected a number of basalts have different underlying mineral composition, and then we measure their reflectivity and emissivity, and we did find that they have very diverse reflectivity for the reason you just mentioned. The underlying mineralogy could be quite different. But on the other hand, the Christensen feature seems to trace the SiO2 mixing ratio in that mineral assemblage. So that's a pretty unique tracer of how mafic or felsic that the whole assemblage is.
Thank you.
Great, thank you so much. And then we have a question from Claire. Go ahead.
Hi, Renyu. Thanks again for the great talk. I also had a question about the spectra of these mineral surfaces. So as you said, the features are due to like things going on with the specific elements in the crystals rather than something broadly about the type of rock. So I'm looking at, like, I think in your spectrum, you showed a feature that you pointed out to be due to Fe2+. And I'm wondering if that's separate than something you would have from Fe3+, and if there's any hope of kind of identifying the Fe2+ to Fe3+ content of these surfaces, or is that not possible?
Yeah, I think the Christensen feature comes from the SiO bound. I think it's come from the bending of that bound. And it is the specifics is impacted by the structure of the lattice and the existence of other things around, like the magnesium and so on. To your question, the FeO2, Fe2+ feature. So I think that the best place to find them is probably the visible light through reflection. So that's not, well, first of all, the olivine has the characteristic feature at I think 1 micron, and pyroxene has has the characteristic feature at 2 microns. So this is from the FEO stretching, I think. But in order to observe this, we need to measure the reflected light spectrum of rocky worlds, and that's unlikely to be something that can be done with JWST just because of the signal is just so small. On the other hand, it is one of the type of planets that the Habitable World Observatory, which is the next flagship mission of NASA going after exoplanets in 2040s, was one of this kind of targets rocky planets in the reflected light is the kind of observations that mission is designed to perform.
Thanks, He.
Great, and we have one more question. Go ahead.
Hi, Renyu. Great talk. My question is regarding space weathering. You were a co-author on a paper by Jintong Liu showing the impact of space weathering on the phase curve of LHS 3844b. And basically, I'm wondering if you think that iron or granitic space weathering could be detectable with spectra, or whether you think it would just introduce degeneracies in our interpretation of surface properties from spectra.
If you think that the main effect of the space weathering is to add some dark material into the mixture, then it will likely to be degenerate with all the other effects that can make the surface darker. I think that paper you refer to based the arguments that the surface weathering could make some surface that are originally bright to be dark, which just based on the brightness temperature measured by Spitzer alone, we cannot infer the specifics of the surface, which I agree a great deal. So I think that the one of the key effects of the space weathering is to introduce either nanophase iron or some other things that make the surface darker. As you say, whether there could be other effects in terms of spectroscopy or phase, I think that we need to study that more. I don't think that we have an answer for that question yet.
Thanks.
Thanks a lot. And then next we had a question in the chat. So Mark Elowitz asks if you have spectra of these minerals as a function of grain size to see how the absorption feature changes.
So we are writing up the paper, and I think that we'll have a figure on that. I think that the contrast of the feature will change as the grain size changes. I actually forget which directions. I think the larger the grain size, the more subdued the contrast will be, and it has to do with the number of the contribution from multiple scatter light that we will see.
Okay, and is it significant?
It is significant
in a hand wavy.
but you have to remember that even for the best object, through JWST, the signal to noise ratio is still limited.
Yeah, that makes perfect sense. Thank you. And then we have a question from Tobias. Go ahead.
Hi, Renyu. Very exciting result. Thank you. I was also wondering about the reflectance spectra of these rocks. You mentioned these experiments that you're carrying out. You also vary the temperature, but I guess you don't reach like the melting points of these rocks, right? Is that something, or maybe you do, I don't know, but is that something you think would drastically change the reflectance properties of the rock, or because could that then be an avenue towards also observing the reflectance properties of lava worlds that do not have an atmosphere?
Yeah, that's right. So our sample reached the maximum temperature of 800 K. So that is they're all solid, very far away from being molten. I think that you're also right that when the material is indeed molten, the reflectivity and the spectral features will change a lot. I think there is one published work on molten surface reflectivity, and I think the takeaway of that is it's both dark and featureless. So so it has an albedo uniformly less than 10% and also a pretty flat black body-like emissivity, which sort of makes sense because the spectral features that we are expecting comes from the vibration of atoms in the lattice, but once it's molten, the lattice will disappear. But I think that this transition from a solid surface to a molten surface, that should be investigated ideally through experiments. It's just that the current setup that we have access to cannot go to that high temperature.
Thanks.
Great. Thank you all so much for such good questions. Do we have any more? And you feel free to write in the chat if you're not able to speak on microphone. Otherwise, maybe I'll throw one out there just because maybe I'll ruin the atmosphere with a more philosophical question. And I'm sure there might not be an answer to this, but I don't have a geophysics background and I'm so curious I can't help myself. Because when you say this magma exchange, the maintained or sustained atmosphere, like, is there any speculation to how long are we talking here? How rare is this sort of snapshot that we're seeing of this planet? Is this something that is going to be happening this week, this month, this millennium? How many billions of years? Is there any kind of speculation on sort of how permanent this type of atmosphere might be?
So yes, we have looked into the escape of volatiles from this planet, and as it turns out, if you work out the numbers, the hydrogen would escape quite easily from the planet. But on the other hand, for most of the history, the hydrogen escape, even if you assume it's hydrodynamic, will not drag the carbon, nitrogen, or any heavier elements along. So much of the carbon, nitrogen, and the heavier volatiles could be retained in that planetary system. So the nice thing about having a magma ocean, rather than a rocky surface, is that this exchange with the planetary interior does not need to go through a crust. So it does not need to have, there's no volcanic outgassing per se.
It's an open wound.
Yes, it's open. Yeah. So we can imagine that this exchange to be more instant compared to a solid surface planet where you have to have some additional mechanism to drive the volcanic outgassing. And this has to do with the ability to observe an atmosphere, because in that magma ocean world, in order to not have an atmosphere, you actually need to remove all the volatiles from the planet, or from the silicate part of the planet. Otherwise, it will get easily replenished from the magma ocean. So that's a much higher bar. Sometimes we do have planets that probably will reach that bar. For instance, there is another planet observed by Michael Zhang. We're part of the observation. We have also obtained a MIRI low-resolution spectroscopy of that planet. So that's a sub-Earth. The planet is smaller than Earth, and it has a pretty high temperature, 1600 K. So it probably has a molten day side. But for that observation, the observation indicates that it does not have an atmosphere. And we also did a similar calculation of the atmosphere escape for that planet GJ367b. And the calculation indicates that it actually makes sense that this planet is depleted of all the volatiles completely. So the escape can remove all the volatiles, all CHOs from that planet, from the entirety of that planet's silicate part. but this cannot be done for 55 Cancri, or is at least very unlikely. So this is consistent with the finding that there is the planet, the 55 Cancri has an atmosphere, and also indicates that, whether a rocky planet has an atmosphere, the mass is an important control of whether a rocky planet would have an atmosphere too.
Absolutely, that's really interesting. Thank you so much. I don't see any other hands up. Going once, going twice. If anyone has any last questions. Because if not, I think we should thank our speaker again. Thank you so much. And I should also mention to you all that the next talk of the series will be on Thursday, the 1st of August at 13 o'clock UTC, at least in my time zone. That's 3 p.m. Central European summertime. And the talk will be on multifaceted characterization of potentially habitable worlds with future telescopes, which will be delivered by Yuka Fuji of the National Astronomical Observatory of Japan, NAOJ. So with that, thank you so much, Renyu, for taking your time to present today for us.